Now, friends, now comes the fun part. Now comes the interesting part about, we can start talking about how fast I'm going. Because so far, if I pick a point on this, these are kind of off-center now. If I pick a point on this graph, it only tells me when I am somewhere and where I am. So at 5 seconds, I'm at whatever I'm at, 30 seconds. Can I change one thing? I'm going to change the y min to, this might not make sense right away. I'm going to change it to negative 25. And I'm going to change the y max to 225. And the scale to 25. And let's see if I can convince you as to why I will do that. This is hardly crucial, but it makes it easier for us to ballpark things on the graph. So I changed the y min to negative 25, the y max to 225, and the y scale to 25. If you press graph, you're not going to notice a humongous change in the graph. As a matter of fact, the only thing that changed, can you see the only thing that changed? These are now tick marks. And they tick mark every 25 feet. Negative 25, 0, 25, 50, 75, 100, 125. The reason I did that is now if I put, for example, a point on the graph and I come across, I have a reference point as to roughly what it is without having to actually go and press the TI. That's just under 75 feet. That's 100. So if I come out to here, does that kind of make sense? Hardly crucial because we're going to use the algebra of the curve in a minute, but just for a visual. So when I start messing with scales on the graphs, you don't feel the need that you have to do it. It becomes very math 95-ish when I do that, which I know some of us are trying to forget, and that's okay. But I like to do that because, like, when I look at the window and it tells me my x scale is 1, I'm a happy guy because that makes sense. Because that means 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. I wish the TI would put a number on there. You know, 5, 10, 25, 100. I wish they would do that. Excel does that. And that's one of the reasons I'm so excited about next week's exam is you have 2 Excel sheets to play with. And you actually see scatter plots and you see stuff in Excel the way scatter plots should look with labels and things like that. So that's why I'm excited about next week's assessment you're doing. Anyway, I'm excited about it right now too. First thing we did was we asked the question, how fast am I going? So what we're interested in is we're interested right here. I want to know how fast am I going here? That's a question I'm asking. Oh, what the hell? It's an exciting question. How fast am I going when I cross that 200-foot mark? When I cross that 200-foot mark. Now you can ignore the parabola past that. That parabola past that doesn't mean anything because I started hitting the brakes right then, didn't I? So essentially I wouldn't have traveled much further than 200 feet. But at that point, how fast was I traveling? Well, this is a tricky question. Because you know, at 10.1 seconds, I've gone 200 feet. But I don't know how fast I was going at that point. That's just how much distance I covered at that point. So what's the first thing we analyzed yesterday? Do you remember? I gave it an acronym. Because the AROC, there we go. The AROC, Aaron. Yes, the AROC. What was the AROC, besides a nod to the Run DMC and the Beastie Boys? Average rate of change. We like those. Average rates of change. This is actually what the little hairdryer that the police use is doing. It's called average rates of change. Let's see how it applies to what's going on with me and my bike throughout this trip. Now we know we started down here at 0, 0. We know that. I believe the first average rate of change that we did was from 0 seconds to 10.1 seconds. I think that was what it was, yes? I believe that was the first one we did. From 0 seconds to 10.1 seconds. Now, when we calculate the average rate of change, when you say rate of change, that's a fancy phrase for what? Velocity or speed. Thank you, Kelly. Both of them are perfectly correct. Velocity or speed. So when you talk about speed of, say, a car, what's the unit you usually use? Miles per hour. Now we don't have miles per hour here, we have feet per second. Yes, we have feet per second. And I want to come back to, I did some quick conversions in class last time using Google. I'm not going to do those first. We're going to leave my speed in feet per second, and then at the very end we'll convert everything to miles per hour to kind of get the point drawn across. Because it's good to know how to use Google. I feel like I was pulling quickly over your eyes, like trying to do something too quickly last time. So, when I calculate my average rate of change from 0 seconds to 10.1 seconds, what I want to know is speed, miles per hour, feet per second, feet per second, feet per second. Does this sound familiar? Feet per... Yes, we take the total number of feet that I have traveled and divide it by the total number of seconds it took me to travel that, yes? So the average rate of change from 0 to 10.1 seconds is actually fairly straightforward. It's 200 feet, and it took me 10.1 seconds to do it, which ended up being what in feet per second, friends?
19.8.
You guys are awesome. 19.8 feet per second. On average. Well, hang on now. Good, good. This is good. The question was, how fast am I going? We took some estimates. It was over 12 to 30 miles an hour. Totally awesome. But the question I have is, what is that 19.8 feet per second? Who wants to use this and this yellow marker and show me what that 19.8 feet per second is actually representing? Anybody feeling creative, artistic, mathematical? Any one of the above? Say that again? I think I got it.
No, 1, 2, 3, not it.
Oh, 1, 2, 3, not it. Got it. Well, so, what it is, and this is not quite long enough, that's okay. I can ballpark it. Pretend that goes to the dot. Oh, it does. Ish. That is related to that 19.8 feet per second. How? How? Say that again, Tom. That's slope. This yellow line is this average rate of change. I shouldn't say that yellow. The slope of that yellow line. Tony, go.
I was just going to say, you might want to use another color. Yeah.
Oh my God! You can't see that at all. God, yeah. Thank you. It looked perfectly great from where I was standing. Let's use green.
That's what I mean.
Let's use green. Thank you. There. Thank you, Tony. There. The slope of that line is 19.8. The unit on that slope is feet per second. So, one answer to my question of how fast was I going when I crossed the 200-foot mark is you average 19.8 feet per second. Is there a problem with that answer?
You weren't actually going that.
Amber, tell me that again.
That was an average speed. You weren't going that speed.
That was good. What assumption does using the average speed from 0 to 10.1 seconds make about my travel on that bike?
That you started at 19.8.
And what happened, Chelsea, I love that. I started at 19.8 and what happened?
You stayed there.
I stayed consistently going 19.8 feet per second the entire trip. 10 seconds later, I stopped. And in that time, I mean, think about it, it's from a slope point of view, yes? From a slope point of view, 19.8, 19.8, 19.8. It doesn't matter what triangle you draw or what small triangles you draw. They all have the same slope of 19.8. So, yes, I averaged 19.8 feet per second. But does that answer how fast I was going at the very end? No. It also doesn't, it negates the fact that I was going 0 at the beginning. So, how can we make our estimate better? I got news for you. We have to use 2 points. We have to get a slope with 2 points, don't we? So how did we make a move to making our estimate better last time? Go ahead, Amber.
Cut it down.
Remember what we did then? We said, okay. I think we did, didn't we? Yes. So what we did next was we said, okay, it doesn't make any sense to start it back here. Let's move closer to the end and use a starting point at the beginning, towards the middle. So I think we used 1, 2, 3, 4, 5. Aaron, you said that, right? So this, we're going to use this time, which is 5 seconds to 10.1 seconds. Okay? 5 seconds away. Just 5 to 10.1 seconds. Now, mathematically, it's exactly the same thing, isn't it? But we do need to figure out that, don't we? We need to know where I was at 5 seconds. And this is where we can use our graph. That should be a horizontal line. Sorry, it tilts up a little bit. My apologies. We'll take care of that right now because we can use the second trace move. Yes? Value. Remember value from a couple days ago? If we type in x equals 5, the TI will tell me at 5 seconds, you were about at 58 feet. You were about at 58 feet, yes? You're about at 58 feet. Okay? So now we can come over here and realize this point is 5, 58. We know my ending point was 10.1, 200. So you can tell my average speed's going to go up because it took me 10.1 seconds to cover 200 feet. This tells me I didn't pick up a whole lot of distance in the first 5 seconds. I picked up most of the distance in the back 5 seconds. Which makes perfect sense. That was the whole point of the model, was because it was getting faster as you let me go down the hill longer. Fair enough so far? Ready for our next average rate of change? I think so. I think we are.
Well, I got one more.
Yes.
A question.
What's up?
Mine stops. Mine doesn't go right at 5.
Oh, you're on the scatter plot. Let's turn him off. The scatter plot gets in the way at first. So now when you do it, it'll get you right to 5.
Oh,
Press second trace value, and then use 5. It'll get you right to it, Kel.
Okay.
Ready? Let's draw that line too. I want to draw it as well. I want to get the visual. Here is my new average rate of change line. Notice, how does it compare? Oh, steeper. Love that word. Orange. Average rate of change on the orange line is much steeper, therefore it's more closely representing what the hell I was actually doing over at the end. It's still not perfect. We're going to deal with perfect soon enough. So now, number 2, average rate of change from 5 seconds to 10.1 seconds. The average rate of change from 5 seconds to 10.1 seconds. How much distance did I cover? Looks like I covered 142 feet. You see how I just did that, friends? I did.
No.
That's okay, we'll do it right now. Never forget your slope definition. Change in y over change in x. Never forget that. Change in y over change. Oh, this is a different question. So what you're really calculating right now is the slope of that line, yes? This is the change in y. This is the change in x. What is the change in y? Well, it ends up at 200 feet, and it started at 58 feet. So the change in y is going to be 200 minus 58, which ends up being 142. That's a 2.
Got it.
Is that fair? Do you guys buy that argument? Is that fair? The change in x is just the change in time. I ended up at 10.1 seconds. But I started counting at 5, which means I was actually traveling 5.1 seconds altogether, yes? Fair enough? So that's, now, if you think about it, you did that same mathematics here. It's just you were subtracting 0 off of both of these, so there was nothing to subtract. I mean, your 0 point was 0, so there's nothing. Please!
Are you saying number 2 is
Number 2. No, we haven't gotten that yet. We're still building it up to that point. I want to start using our TIs to get that number. I mean, and we're using our TIs a little bit. I want to use it even more directly to get that number. We're not even back to the quiz yet, friend. Not back to the quiz yet. So, what does this end up being? This is feet per second, of course. What does it end up being?
27.8.
27.8 feet per second. So you see an increase of about, I'm going to call it a third, but that's probably being too generous. Fair enough? Ask me questions if something is still, I want to make sure we get the mechanics checked off here. I don't want to get you guys freaked out about mechanical differences. All we're going to do, and the rest of the quiz does this, is we're going to keep sliding that first point closer and closer to 200, and closer to 10.1 seconds. And what's going to happen as we take that point and slide it closer and closer? What's going to happen to the line? It's going to keep getting steeper and steeper, and the closer we get to that end point, the better the estimate of my actual speed is. Is this a good estimate of what I was doing at the end of my trip? It's still not good. It's better than the previous one, but it's still It's still not very close to the actual curve. The curve that's under there is what's actually going on. My distance and my time. Distance is a function of time. I'm still approximating it with a straight line, yes? I'm still approximating it with a straight line, which is going to be a problem. I can't actually, the curve is a curve. A line is a line. A line cannot equal a curve. But if you sneak the line close enough to the point you're interested in, the curve will look like a straight line. Well, we're going to mess with some zooms momentarily and prove that to you. If you zoom in on that curve enough, small sections of it look linear. When you pull back and look at the whole thing, it's curvy. I hope I didn't upset anybody. It's getting close to lunch. This might be a lot on an empty stomach. But those curves are curving, yes? But so is the planet we live on, correct? So is the planet we live on. Have you ever just gone walking across a small section of forest and go, oh my God, it's so flat right here. It's not flat right there. It's actually curving right there. You can't perceive it because you're zoomed so far in, so far close. But if you try to, say, for example, measure Mount Hood from Bend, then you have to concern yourself with the fact that the Earth is falling away from you over 3, 4, 5, 10 miles. So it's that whole idea of relative perception. When you're really close in on a large curved object, it looks straight. It looks flat. But as you pull back, you're like, oh God, there's the world it's round. Kind of thing. Fair enough? Same thing happens on a small scale, this parabola. Fair? Ish? Good? Maybe. Okay. Now what I want to do right now, I'm going to stop and start the camera again because we're going to learn a cool TI trick. We're going to learn a cool TI trick.